My name is Yanfei. I'm an assistant computer scientist at Argonne and on the MPI team. So the next few topics is going to cover the MPI hybrid programming. The first one we're going to look at is the MPI plus thread. But just as an overview, the hybrid is not limiting to just MPI plus thread per se. So this is commonly referred as MPI plus X, if you will. So basically, traditionally we have the flat MPI, these just running process on the CPUs, and it's all very, very simple. But the hybrid models is the common ones are the MPI plus thread, MPI plus ACC or accelerators, and MPI plus shared memory. So in this tutorial, we're going to cover the MPI plus threads and MPI plus ACC, especially with GPU as the accelerators. The MPI plus shared memory, we're not going to talk about that, but if you're interested, I'm happy to chat over it after the tutorial. Okay. So then the reason is why people have been using MPI for a very long time and seems to be happy with it, and why suddenly we're starting to do hybrid program models. So one reason is how the hardware is scaling and evolve over time. So as you know, that we're just simply cannot just cranking the CPU to higher frequency and then scale out easily. We after a certain point, we started to build more CPU cores into the machines, and each node getting more CPU cores. But however, at the same time, the other resources like memory and network bandwidth, they didn't scale in the same fashion as the number of CPU cores. What you end up with is you getting more and more CPU cores, but if you look at the memories per core, if average out, memory per core, you're actually getting less memory compared to before. So and also because there's so many processes on the same node, doing MPI communication between them is relatively costly compared to just simply do load store. Although in any good MPI library, download communication should go through shared memory, but still you have to prepare the necessary data structure for the MPI communication. And also because this huge number of CPU cores, if we just blindly run process on them, it means a lot of the collective operation is going to be dealing with a huge number of processes, which may not be easily optimized to have a good performance. Okay. Yeah, like I said, this scaling problem is actually pretty true. Like I said, you don't. If we're using MPI plus X, X being thread in this case, we do get some benefit. Now instead of dividing all the memory into each processes, now if I run one process on the node, and that process will be able to use all the memory, and if I parallelize the computation using threads among them, then the communication or data exchange between the thread essentially became load store. It will be much faster than MPI. And at the same time, because we're reducing how many processes are there in the entire machines, and it's also reducing the complexity for communication by a certain amount of factor. So a good example is NEC 5000. Basically, NEC 5000 is a computational fluid dynamics application working with strong scaling. Basically, by reducing the number of, by employing a hybrid MPI plus thread and reducing the number of processes on the run, it significantly improves the performance of collective. And another example is QMC pack. So this is more on the memory size, side of the thing. Basically, for QMC pack, you need a large bit-spline table for each process. But these table can be shared by different processes. So if you instead of running one process per core, if you do one big process on the node, and all the threads, computation thread can share the bit-spline table, which allows you to host a much larger data than comparing to the process-only version. Okay, so how to do that? Like I said, all you need to do is, instead of launching one process per core, now you're thinking about launching one process per node or one process per NUMA node, depending on the architecture of your machine. And within that node, you just run a bunch of threads. So if you recall our stencil example in the tutorial, one of the extra benefit with this is you have to allocate less memory for the halo region, because if you compare these two setups, on the right hand side, the reduction of number of processes basically reduces the surface area of each of the overall process data domains, which means you have a smaller halo region. So usually the thread level basically, when you're trying to program with MPI plus thread, basically you're thinking of two levels of parallelism. Okay, so in this case, MPI is going to handle all the parallelism happens across processes. So that means basically these are separate address space, which is why you need a massive passing to communicate, to exchange the data. And at the thread level, it's going to be the same thing as you probably did yesterday with the OpenMP tutorial. That's you can have a bunch of threads and work on a shared memory region that contains all the data that you need to compute with. Okay, so commonly with MPI you can use pthread or OpenMP directly. Both are commonly supported. One important thing to notice is the what we call the MPI plus thread interoperability level. So in MPI standard there's 4 levels of these interoperability. So basically there's MPI thread single, thread funnel, serialized, and multiple. So the higher level means there's less support for threading. Means you also have more restriction on how you use MPI operation with threads. But the benefit is that it's usually lower overhead because MPI has to do the restriction of how you use MPI operation with thread basically allows MPI to easily optimize of these cases. Where if you go deeper, go down, you have more flexibility. Basically, has almost no restriction on how MPI operation can be used within threads. But then, because all the thread safety requirement and the MPI's communications requirement, the library MPI have to do a lot more work to make sure that works correctly, which in turn incurs higher overhead. So, yeah, and the last thing to mention is if you want to use MPI plus thread, there's one big thing that you need to do is initialize MPI application with MPI init thread, not MPI init. Although in reality, if you do MPI inits, it probably works with many of the MPI library, but it's still an incorrect program. Okay, so the MPI init thread here is taking 2 extra parameters. there's a requested MPI thread support level, which is one of these 4. And then the library is going to return you a provided one. So basically, for example, I can say my application request for thread level MPI thread multiple, which means I want the maximum flexibility. But I might have a very old version of the MPI library, and it doesn't support MPI thread multiple, and it will probably just return, say, I only support MPI thread funneled. So the reason for this design is, one, allowing MPI library to have some flexibility in implementation, and also this gives a application a chance to say, hey, I want a thread multiple, but maybe my application can also work with thread funnel, so you can fall back to a different design in order to get a better availability on different machines. Okay. So the simplest one is MPI thread single. So this model is basically saying I'm not going to use threads. The reason of having it here is what this level is doing is you're basically doing MPI process only MPI, but specifying this level, this thread level allows MPI to use thread safe library. So if you have a third-party library that internally uses a thread, setting this, although your application doesn't use thread directly, but it will tell MPI to use thread-safe external libraries. So that's pretty much just that. So the second level, that this is where we start to use threads in our application. So MPI thread funneled, basically saying that you can use thread for whatever you want, but the MPI communication can only happen in the master thread. So the master thread here is whichever thread is calling the MPI init thread. That thread is going to be the master. So in this case, basically, if you look at this example, we have a very small thread function here doing the computation. And on the master thread here, we just create a bunch of this computation thread and wait for them to finish before the master thread doing anything MPI. So maybe an MPI send here or an MPI receive. Okay. So similarly, the next level is called MPI thread serialized. At this level, we're still only allowing one thread to make MPI call, but the restriction has been relaxed to that you can use any thread can do MPI call, but only one of them can be doing MPI at a given time. So basically, if you compare to, if you look at the thread function here, now we have moved the MPI stuff into the thread function. But we're protecting it using a mutex lock, so we're guaranteed that only one thread is doing MPI call at a given time. So this is basically gives you a more flexibility in terms of programming. Okay, and the last level, which is the most flexible, is thread multiple. Basically, just do MPI stuff in the thread, and you don't need to explicitly coordinate between the thread. Although there's other requirements that need to be satisfied in this model, but we'll talk about that later. So these are the quick overview of the 4 threading models. So like I mentioned, this is fairly simple. So for most of these cases, if you use thread single and thread funneled, you can think it as traditional MPI program plus some benefit with thread because you're using thread for computation. So when you program it, it's not actually quite different. It's pretty much the same as you would with a pure MPI process-based application. So there's not much special care that you need to look at. But at the same time, if you venture into the MPI thread multiple realm, there's a lot of semantic, MPI semantic related stuff that you need to be careful about, which we'll talk about later. And lastly, remember to initialize your application with MPI init thread. So far, any questions? Do we have any questions on the Slack channel? Oh, yeah.
So just if you go back 2 slides or so, you always have the P threads in there for loops. If I was to use OpenMP, could I just put a OpenMP parallel 4 around it, and that's it?
Yeah.
Awesome.
Yeah, although you would need to use your OpenMP's pragma to synchronize between the threads. But yeah, this if you're not using pthread create, but using OpenMP, as long as you somehow coordinate between these threads before they do anything MPI, it'll be fine. Yeah, so pthread is only for the simplicity as an example here. Sure.
I think it's a few more slides back. There was one thing saying that thread level increasing order or something like that. Maybe later. Yeah, the middle one.
Oh, yeah, sure. Yeah, that's right. So yeah, that's a good catch. So the thread level support is in a, so there's 4 levels and there's an increasing order. The closer you get to thread multiple, you have a more flexible. But it also means that anything with any application designed for a lower thread level should work with higher thread support, no problem.
Yeah, so like if the application works in the funneled mode, which means it has more assumption or restriction about which thread is actually communicating, right?
That's right.
Then how can it work in the serialized mode? Because that doesn't have that assumption.
Oh, so this is it's the other way around actually. So the lower level MPI plus thread application will have more self-restraint. So it's, yeah. So think about this. If I have an application designed for a thread funnel, which means it's only be one thread, and that one thread will be the master thread with doing communication. So if I put the same application in the thread serialized mode, although thread serialized mode allow me to do more, but I'm not doing that, which means the application should still work.
So it's the programmer's responsibility to make sure the master thread is actually communicating, not the MPI implementation?
That's right.
Okay.
Yeah, so which is why you compare the thread funnel and the thread serialized, you will see that the thread funnel, the communication is still outside of the thread function, where in the serialized, it's inside of thread function. Like think about this, if I only launch one thread here, right? Any more questions? Go ahead.
What's the risk of using an MPI thread funneled program without declaring it? So, I mean, basically, if we do a fork, then join, and then do the MPI communication, what's the difference between using MPI with only one thread? I'm not sure if my question is clear.
Yeah, so like I said, it's not this is mostly related to MPI's internal management of what kind of thread-related resource are available. So if you just launch one thread and that thread not being not the master thread, there's internally there's it could be a different set of resources that need to be dealt with, which is why there's two different levels. And in reality, if you choose the thread, if you only launch one thread, why are you doing a thread at all? You can go by with MPI processes, right?
Yeah. And MPI also makes calls to system routines and other things internally, and it might need to make calls to the thread safe version of those. So even though you are calling everything from one thread or the MPI calls, if you don't declare it properly, some of the internal system calls, etc., that MPI makes may need to use the thread safe or not thread safe versions of those. So it's for an out of abundant safety that it's defined.
Okay. No more questions? Okay. So the next set of slides, we're going to just focus on the MPI thread multiple, which is there's a lot of fun related to MPI semantic. As I said, the MPI thread multiple allows you to make any MPI call within the threads without explicitly coordinating, but there's certain requirements that your application need to match in terms of ordering and progress, which is important to the correctness to the application. Okay, and so one thing, so for the ordering, because you're now doing MPI application MPI calls inside the thread, the relative ordering between the MPI calls is only maintained within that thread, right? So think about this: if I do MPI ISON in two different threads, the ordering of which one happens first is completely depending on which thread gets scheduled first. So the MPI has no way to control that, and but if you do MPI ISON, two MPI ISON in one thread, that the ordering between that ISON is guaranteed. So and also on the progress side, since all the blocking MPI call now is only going to block the thread that's calling it, so it's not going to block the entire application. So that's it's the same behavior as any blocking call that's being made in the threads. Okay, so one of the ordering example is here. So we have two processes, and each of them have two threads. So one thread is doing MPI bcast, and the other is doing MPI barrier. So as you might remember, that's in MPI these calls need to match across the process. However, because the ordering of MPI call between two threads are not guaranteed, so it's possible that for one of the process is doing bcast first, and the other process is doing MPI barrier first. In this case, this will be an incorrect program because these two, from MPI's perspective, we have two non-matching collective operations being called together to cause a deadlock. Yeah, like I said, if one thread gets scheduled earlier than the other, it became a incorrect program. And another example is freeing communicator before you're doing any communication on that communicator. So this also could happen because of how threads are scheduled. And here's another example, which is actually a correct program. So both of the process is doing send receive, where one thread is doing send and the other other thread is doing receive. And in this case, we're using a non-blocking. We're using blocking point-to-point communication here. So regardless which thread getting scheduled first is going to block that thread, but that doesn't prevent the other thread from running. So at the end of the day, these application would complete correctly because both send and receive would be issued. So basically, I think there's one. So just to quickly summarize about the ordering stuff, the takeaway for this is your application need to have a correct ordering regardless how the threads are scheduling. So this is actually a fairly complex requirement on the user side because as we will see in the next few slides, there is actually a very interesting example that the user run into and reported to us, and it's a fairly complex one. We'll see that. So basically, this is not easy a easy one to get done correctly in the application, which requires special care when you design the application. So currently on the support on the availability of thread multiple and the other thread level in the MPI library. So most of the library is supporting thread multiple, although and also the lower level including thread funnel and thread serializer. Although sometimes they may not report that way. And also, if you think about porting a OpenMP application to use MPI to scale across the node, then the minimum requirement that you have is you can have a thread funnel and just treat the computation part with the threads. So that will be easy to start with as a box synchronous applications. And again, should I be using MPI plus thread is totally depending on whether your application needs it, because it's not necessarily simplify your application design, because you experience this firsthand from our example. So it's more important that you think about whether this is a good model that works for your application, rather than just say, hey, it seems cool things to do and let's do that. Okay. But the good thing is many commercial debugger and profiling tools already have good support with hybrid programming like MPI plus thread. So it'll be important to have those tools and play with it while you're writing your programs. Okay, so this is the perfect example and proving that getting the ordering exactly correct is very complex. So this is a very simple program. It only runs 2 processes. Each process gets 2 threads, and the user reported the bug, and took the team very long time to figure out where the problem is. We thought our library has a bug, then they only realized the user program was incorrect. So this is the communication that happens in the user program. So for each process, depending on your rank 0 or rank 1, you're going to run the green code and or the red code. But each these chunks, the green chunk and the red chunk, are run by 2 threads in that process. Basically, it's going to do 2 send and doing 2 receive, and do another 2 send, 2 receive from each of the thread. So if you draw them out, this is what the ordering that the programmer has in mind when he writes the program. Basically, having one thread talk to the thread 0, talk to the thread 0 on the other side, and thread 1 talk to thread 1 on the other side. So that's what it should be doing. But this code running on real machine runs into deadlock. Can anyone think of why this could happen? Okay, so this is what could happen and actually happens on the machine. So the first set of exchange threads T1 is doing receive 2 cents, and on the other process T1 is do 2 cents, but only able to do 1 receive before it get descheduled. Okay, and then the thread 2 is doing 2 cents, and at the same time on the process 0, T1 is being able to do 1 receive and then descheduled. What happens here is these 2 matched together, okay, and these 2 cents from T1 on rank 0 get matched by different threads on rank 1. Okay, so that's the first step of problem. And then the 2 cents on the T2 get matched by 2 different threads on rank 1. And then the next step, if you look at these threads, every one of them is doing a receive, and this is blocking call, and is blocking all 4 threads, because everyone is waiting for someone to send, but no one is sending. This is actually caused by a problem that's, if you would, MPI doesn't have a concept of thread. So although the user intent for different thread to talk in pairs, but if you look at the function call here, it only specifies the rank as a process. There's no indicating which thread should be getting these messages. So it basically allowing this situation to happen, right? Because anyway, if the message arrived to the different process, any of these threads, if they have a receive that matches this this message, is going to take it. So a simple way to solve this problem is you can use a thread ID as a tag parameter in your operation. So then the message from the T1 on rank 1 that targets for T1 on rank 0 that targets for rank 1. Instead of saying 0 as a tag, you can use T1 as a tag. So in that case, on rank 1, the T2 would not be able to match its receive to the one that has a tag saying that is going to T1. So that would be an easy solution for this, basically using thread ID as a tag. And alternatively, they can also be using, for different pair of thread can also be using different pair of communicators. So the traffic between different communicators are also isolated. It will prevent the T2 to intercept the message that is going for T1 if they're using different communicators. Okay. Any question about this? No? Okay. So that's the basic requirement for MPI plus thread to work correctly. And the next, we're going to see some of the example of these correctness-related stuff, particularly with OpenMPI, particularly with MPI plus OpenMP setup. So, okay. So this is the first example. We basically have a OpenMP parallel for loop, and for this for loop, we're basically doing an MPI send and MPI receive, depending on the iteration that we're at. Basically, all the iteration we're sending data, and all this iteration we're receiving data, and even iteration we're sending the data. Okay, so is this a correct program? Anyone? No? Why is it not correct? Okay, so so this is, remember that the iterations are mapped to different threads. This mapping is controlled by the OpenMP library. So what could happen is it decide to map all the it generates a map of iterations to thread where every thread is starting with a even iteration, which means everyone is sending, no one receiving. The program will deadlock right away. Okay. And a simple solution for this is instead of having OpenMP to randomly decide how this is going to happen, you can use the schedule to specify that that each thread getting one iteration. So that would help this problem. So like I said, by explicitly indicating how the iteration should be distributed to threads. Okay. And another example is with OpenMP tasks. So it's the same thing. We have parallel loop, but now we're doing OMP tasking here. So is this a correct program? Okay. Yeah, it's still not. Basically the same problem, right? Whether this task getting other iteration or even iteration, and how that task is being scheduled to the thread is gonna determine whether all the thread is doing send or MPI send or MPI receive, or is any one of them is gonna match in this case. So then you might think, okay, how about do I use OpenMP test loop to address this? This is still a incorrect program. It's exactly the same problem before. Then you will say, oh, because you're using blocking operation, right? What about if I'm using a non-blocking operation to replace the blocking send and receive? In this case, it's still an incorrect program, because instead of using blocking MPI calls, you basically just move the blocking point from the send and receive itself to the wait. But again, if everyone is doing an isend and then do an MPI wait, it's the same as doing MPI send itself. So it suffers the same problem with the previous example. And now this is an interesting one. So now you're thinking about, okay, so I'm not doing, because I'm using a blocking completion function. What about if I just do a while loop in my task and using MPI test and try to yield from it if it's not done? This is actually a good thought, but it's incorrect because the test yield itself does not guarantee a task switch. So it can still be running the same task on the thread. And lastly, this is actually the correct solution for this problem. Basically, it's only using non-blocking operations inside of each task. And instead of waiting inside the task, we just let the task run and issuing all the communication operation. And once we're out of the parallel region, we do MPI wait all for all 100 requests. Basically having 100 on-the-fly operation for, and we just do a batch wait for them to finish. Okay. And similarly with thread multiple, RMA is the same thing. So in this case, we're basically the MPI win log is going to be locked if everyone is trying to lock the same target. So it's a similar issue with the blocking send and receive example. Okay, so far, is there any question about the MPI plus thread before we go into the examples? Okay, so now is the time for us to see how our stencil example can be modified into using MPI plus threads. Okay, so we have the first step is pretty simple. Let's just do a thread funnel mode. So in this case, we'll be using the master thread for communication and using OpenMP threads for the computation. So it's pretty much just the same communication halo exchange, but launching multiple threads to calculating on the white region the data that each processes own. So if you look at the code, so the communication part is pretty much the same from the derived data type. All you need to do is take the derived data type version and try to use OpenMP to parallelize the computation part. So if you look at the derived data type code, you will see there's a function called update grid, which encapsulates all the calculation that is required for it. And what you need to do is move that part into the main function and use OpenMP to parallelize it. Okay, so how about we work on that? So let me just walk through the solution with you. So if you go to the code example here in the threads, we have stencil funnel.c. So this is the stencil version, the funnel version of the stencil code. Okay. So is this large enough? Maybe I should zoom out a little bit. Is the font size still okay? Okay. So like I said, this code is largely based on the derived data type version. As you can see here, we're still creating derived data type for the communication. The biggest difference is here we started to have a parallel region, OMP parallel region for the big iteration loop here. So first of all, since it's parallel and having multiple threads, first thing that we declare here is the loop counter here being private to each process, to each thread. And since then the next step, before we run wild with the computation with threads, the first thing we do is we use the pragma OMP master here, indicating the rest, the next code section is going to run only on the master thread, not all of these threads. Okay, so again, and this code is pretty much the same communication code as the derived data type version. So first we refresh the heat source for this iteration, and then we're exchanging the data with our neighbors. So there's the full ISIN and I receive here. So once they're finished, we have all the updated boundary data. Then we can go to the next step. So here we're just using a OMP barrier to synchronize all the thread that is in this parallel region, and then here is where the parallelized computation happens here. Okay, so here basically if you comparing this loop and and the loop in the update grid function. You'll see this is the same loop, except for now it's a parallel loop in OMP, and we're using one declaration here as reduction, indicating the results of the heats need to be summed together for the parallel loop. So that's basically the parallel part. And then lastly, we go back to our master thread, just finishing the exchange of the old and new matrix working array. And then at the end of all these iterations, we're going to print the result into the graphics that we have. So this is all for the parallel region, and the rest is pretty much the same as the derived data type version. So as you can see, if this is complex in a way that because we're moving from a process-only version and to a MPI plus thread version. But it's also possible that you may have an application today that's already using OpenMP to parallelize on a single node, but you want to extend that application to multiple nodes. That's the other cases that you can encounter, which means in that case you probably already have this parallel region here, this parallel 4, and all you need to do is add the other parts with the, for example, the OpenMP master region that is used for communication. Once you have this, if you want to further improve this application to use thread multiple, then it will be much easier to do this. So I would say if you want to port an existing MPI application to use thread, or an existing OpenMP application to use MPI plus thread, thread funnel model is your first stop. This will give you a working version that you can at least verify, and then think about how the performance can be further improved using thread multiple. Okay. So any question about the example? Yes.
Is there any particular reason for master over single?
Yes, like I said, we want to use them because it's thread funnel. We want to use the master thread to do the communication, and since we're calling MPI init thread in here before the parallel region, we want to use the master to yeah. So if you do serialize, you can use single, of course. Yeah, go ahead.
Is there a performance impact on using funnel versus multiple?
There shouldn't be noticeable differences in here.
Could you explain why you use the schedule? Why you use schedule in the OB4?
That's actually a good question, because I'm not sure about the answer about the schedule here.
Iteration in the loop is doing the same kind of work, so there's no reason to use a dynamic schedule.
No, it's in like since the actual dynamic is useful if the amount of work being done in each iteration is unknown ahead of time. But since it is known, we know exactly the flops that are happening. You can just do a static and avoid the overhead of doing dynamic. But
right.
But it's optional, I think, is the main thing.
Okay.
Okay. Any other questions? No? Okay. So that's our funnel example. Let me switch back to the slides. Okay, so apart this thread funnel version, we also have a thread multiple version. I'm going to just talk about it, but we'll probably skip these hand-on parts for now. We can continue to do this after covering other content. So once you have the thread funnel version, the next step of evolution will be try to make it into a thread multiple version. In this case, in addition to the existing domain decomposition for the process level, now we have to think about how we're going to decompose the data region for each of the threads to handle. So here's just a simple example here. We're basically breaking this 2D array into 4 big chunks and having each of the thread to handle a part of them. Then, because it's thread multiple, each of the thread would also be responsible for sending the boundary data that belong to them. Although there's more than one way to split this region. If we're talking about 4 thread in here as an example, we could also do a 2D decomposition of the region instead of a 1D. Then in that case, each of the thread might have a more even amount of boundary data that need to send. Because in this case, if you look at the leftmost and rightmost thread, they would need to talk to 3 neighbor processes, and the middle 2 threads only talk to the north and south neighbor, right? And but if we do a 2D decomposition, then each of them are talking to 2 processes and with roughly the same amount of data. That might be a better design, having a more balanced communication pattern for each of the threads. Okay. So Halo Exchange is also decomposed in this case. And again, we're going to skip the hand-on just for now to look on the other contents that we're going to talk about. So MPI plus thread performance recommendation. So this is mostly related to thread multiple. So one reason that MPI plus thread with thread multiple is not widely used is that historically performance is pretty bad because it gives the maximum flexibility to user, but it means MPI internally has to do a lot extra work to make sure the communication happens correctly, which introduce a lot of overhead. And because performance is not great and people are not really excited to use that, which leads to a vicious cycle that no one is actually putting a lot of effort to optimizing that performance. So less and less people are interested in using that. But that was history because right now I think at least for MPI-CH we have a pretty good optimization available if the user would able to program the application in a certain way. So here's our recommendation. So basically the idea is you want to have the maximum independence between thread when you design the application. So for example, one way to do this is for each of the thread to use different communicator. The reason is that this not only allows you to isolate the traffic between the different threads, which makes your program less error prone, unlike the one that we just see a few slides ago. But it also allows the MPI library to optimize this communication under the hood. So what the modern network hardware has is they could have multiple communication contexts that is available in the hardware. So basically, they could have multiple hardware queue for for your outgoing and incoming messages. So these are, because these are separate hardware resources, so if your thread is using different resources, then the library don't need to have a lock to protect this region, right? Because they can be assigned to different hardware resources. There's no contention between each other on the shared resource, hence no locking overhead. But at the same time, because MPI has no idea that you're using threads, so this is more of a way that's telling MPI that you're having different traffics. So basically, MPI the traffics in different communicators are isolated. So what MPI can do is it can map the traffic from different communicators to different network communication contexts. So in that way, it's indirectly maps your thread to different set of network resources. So that's an easy one. And at the same time, this kind of mapping can also be done with tag instead of communicator if you don't want to create a communicator for that. So it's a similar case where the MPI can look into the rank and tag combination and decide, oh, this is a separate traffic flow, and then it can be mapped to a different set of resource differently. And the last thing is there's any source and any tag parameter that you can use with MPI communication. This can be very convenient, but at the same time, this is the hardest thing for multi-threaded MPI for MPI library to optimize for multi-threaded communication. Because, for example, if you have any source, any tag receive on a thread, and the messaging, MPI would have to maintain the messaging order of your incoming message, because the receiver side have no idea to know whether this is a intended ordering from the sender or is just it's random. So you'll have to assume all these ordering are important, which means regardless how many threads that you have that can receive the message, the library itself would have to queue all these incoming messages together to maintain the order before any thread can come in and claim these messages or match to these messages. This is really hard because it creates one big bottleneck on the receiver side. Because if you think about the sender might be just sending these messages from different threads, and the thread can get scheduled in any order, so that the arriving order doesn't really mean anything to the application. But MPI has no way to do that, no way to understand that, which is why we would recommend you to use the info hint to say there's we're not using any source or any tag, these wildcard parameters for a communicator if you don't need them on the communicator. And in that way, it will be much easier for MPI to optimize the communication for multiple threads. All right. I'm going to skip that. So this is what MPI-CH library does today. So if you use MPI-CH and any new vendor library that derived from MPI open source code, you'll have this. This is what this is called virtual communication interfaces. This is not user visible. It's completely internal data structure, but each of these VCI can be representing an independent set of hardware resources. And your communicators, different communicators can be mapped to different VCIs. That's how we can isolate in MPI-CH to isolate the traffic from different threads to give you better performance of thread multiple communication. And similarly, we have a code example that you can try with using multiple communicator in thread multiple. The code is in there. So basically, if you want to try this after you finish the stencil, the thread multiple version of the stencil code, you can also try to extend that into a multiple communicator ones, which is a very simple change to do. So as you can imagine, if you do have an MPI plus thread application that you want to get good performance, this is something that you want to try with. Just some quick example of how these improvement by using multiple communicator can have, how much improvement you can get from using multiple communicators. So as you can see here, the light blue line here on the right hand side, the top one, that's the no threading at all, just MPI processes. This representing the maximum message rate that we can achieve using the MPI library on this particular machine. And if you look at the red line, that's thread multiple using a single communicator. In this case, it's since it's a 16-core machine, that means we have 16 threads basically competing. And the message rate is completely horrible, right? But if you compare it to the other lines here, especially the purple one, where we have multiple communicators, as you can see, we're getting almost the same performance to the non-threaded version of MPI. So this is what the Intel MPI that you can use can get the performance. So the takeaway for this is always try to use different communicator or different tags to isolate your traffic, and in this way it would indirectly expose the thread level parallelism to the MPI library. So the library can do optimization on it. And if the library doesn't have optimization on it, it's not going to hurt your performance anyway. So that's everything I have for the MPI plus thread. So do we have any questions before we jump into MPI plus GPU? Okay then. The next thing we're going to talk about is MPI hybrid programming with accelerators. And specifically in this case, we're talking about MPI plus GPU. So one big reason that we want to use GPU is GPU is high flops, relatively comparatively low cost and low power consumption, considering how much computing power that we can get from it. It's completely different model. It's using their parallel execution model versus a test sequential model on the CPU. And also, as you probably already noticed, all the futures supercomputers, exascale supercomputer in US is going to be GPU based. And as a matter of fact, Frontier, the current #1 machine, is already online, making the it will be impossible with the power constraint and out constraint to reach the 1 exaflop mark without using GPU. Basically, you can see that's all these new machines with GPU. So again, similarly, because the GPU is adopting a quite different program model than the traditional CPU programs. So programming with MPI comes with certain requirement from the library and also from the GPU programming models. So so for most of the GPU, we'll be dealing with a vendor-specific program model. For example, if you're using NVIDIA GPU, then you'll be using CUDA, right? AMD GPU, then you're talking about ROCm. And at the same time, OpenMP is extending its capability to support offloading to GPUs, but that will be beyond the coverage of this tutorial, and similarly with the OpenACC and OpenCL. So the main problem with the MPI plus GPU is how these GPU programming models can interoperate with MPI. Specifically, the question is, how do we move the data between GPUs using MPI, right? As you can see, the introduction of the GPU is basically we're having a different set of memory on the GPU device, which is not accessible as the same way as the main memory, while at the same time the MPI is mostly designed for CPU memory. So how do we do that? We basically have to consider several different types of data transfer or communication. One is on the same node between the GPU memory and CPU memory, if you have, or how to communicate over the network to a remote node's main memory or GPU memory. And at the same time, if you have multiple GPUs on the same node, you might also need to the MPI also need to handle the communication that happens between the GPUs. If you have multiple processes and each of them have their own GPUs and they need to talk to each other. So the short answer is, if you are not using a machine that's 10, 20 years old or a GPU that old, you probably it will probably be fine to just use a GPU memory pointer in the communication, and the MPI library would be able to handle that, since at least all the major MPI libraries today should have a basic level of support for GPU. But again, the real answer is depending on what GPU you have and what is the version of the driver that you get on the system, whether a appropriate kernel module has been loaded, and also the MPI implementation, you might get different level of support and different kind of performance. So most of the GPU support today is relying on the Unified Virtual Addressing, UVA. Basically, it's allowing the GPU memory and the main memory to share the same addressing space, so that we can be easily take a GPU pointer and using the GPU library to query whether this is a GPU buffer and a CPU buffer, and then MPI can take care from there and to make the data transfer. So there's multiple different ways, right? So there's the most rudimentary and case is where we have to do a double copy. But basically, there's no hardware support between the GPU to give the access from the GPU memory to the network card. What MPI is going to have to do is either using MPI will have to create a bounce buffer in the main memory for both of the single and double copy cases, where the GPU would have to move the data into this pin memory, and then the network card can take it over and send it over network. The difference between the double copy and the single copy is whether the DMA on the machine is allowing the data transfer from a GPU buffer to a pin buffer on the memory, or if it needs a separate GPU pin memory to as another bounce buffer for this transmission to happen. But for most of the new GPUs today, you'll be looking at the last one, where the zero copy case, where the GPU the GPU memory can be directly accessed by the network card. Okay? So this will be the most performant case where we don't need any involvement of CPU to help the data movement. And also for intranode, if you have multiple GPUs, it'll be great that if the GPU can talk to each other without using the CPU. So this is generally done by the IPC capability of your GPUs. So what is going to happen is in this case, if you have two processes, each of them get their own GPU, and if there's communication need to be done between them, the MPI library can take the source buffer and create an IPC handle. So instead of sending the entire data through PCIe bus and through a shared memory transport on your main memory, the MPI library can simply just send the IPC handle to the other process, and then that process can use this handle to read or write from the source buffer directly. So this is especially beneficial for large size transmission. So these are the interoperability possible with the UVA. So another possible way to support MPI plus GPU is using the heterogeneous memory management capability on the Linux kernel. So what this is, basically the operating system can migrate the memory page between the GPU memory and CPU memory. So in that case, if we need to send data from a GPU memory to a remote node, then the operating system can come in and migrate the page to the main memory before sending over a network. This is in CUDA. This is also possible with the unified memory. This is fairly simple to implement on the MPI side, but it's actually really hard to get good performance because this is basically depending on where the page is, right? So if your page on the host memory and you need the data in the GPU memory, it incurs a page fault and there's overhead move the page around. So for that to be added to the latency of doing communication, it's actually pretty expensive. So for most of the MPI implementation today, we're not taking this route. So most of them are relying on the UVA one. So the next few slides, we're going to show you how this can be done with the CUDA, and NVIDIA GPUs. So just a quick overview of how CUDA is. This is the programming model for using NVIDIA GPU. Basically, you write a GPU kernel function for any computation that you need to do with the GPU, and you launch it. That's it. And the important thing to know here is the kernel launch. The kernel launch operation here is asynchronous, right? So it's not going to the main function is not going to wait for the GPU kernel to finish before going to the CUDA mem copy. Okay, which is important for in the next few slides, as you can see. So if you have very old version of CUDA library, that means CUDA 4. In this case, there's no GPU direct RDMA support, which means MPI would have to create a bounce buffer in the host memory for the transmission to happen. But from the user's perspective, you can already use the device buffer as a function pointer in in the MPI function. It's just that the MPI internally would have to do extra memory copy from the GPU buffer to the main memory. And also, as I mentioned, the GPU kernel launch step is asynchronous to the host CPU, which means you would need a explicit synchronization between the CPU and GPU, in this case a stream synchronize, before you doing MPI-SYN. Otherwise, the kernel launch would complete, and then immediately the MPI-SYN would try to send the data while your GPU kernel may or may not be running on it yet. So it will get incorrect data. So then similar code would also work with starting of CUDA 5. But at that point, it will already have the GPU direct RDMA. So in that case, it will not be using the temporary buffer for that. And similarly with MPI plus unified memory, if you want, but be aware that there might not be a good performance because the incurred page migration of unified memory. So just a quick summary. As I said, if you don't have a more than 10 years old GPU, you'll probably fall into the middle case where you at least have the GPU direct RDMA, which means there's no extra copy. The data, it can directly go from the GPU memory to the network. And all you need to have from that is a GPU-aware MPI implementations. Just a quick summary of what kind of hardware and software combination that you have with GPU direct RDMA. You need at least new enough Mellanox hardware for this particular purpose. And also you need to have a new version and a compatible version of Mellanox OFAD, because if you have a slightly older network, for example, Connect X4, and you want to use the latest Mellanox OFAD version 5.x, you'll find that they have dropped the hardware support for older hardware, which means you don't get GPU RDMA in there. So in that case, you probably want to revert to an older version. And also, you need to have the correct GPU kernels and GPU drivers and kernel modules, which one of the important things is the GDR copy, in this case, to actually have the GPU direct RDMA to work with a GPU-aware MPI implementation. So just to summarize, GPU is getting more and more popular, and from the user perspective, if you have a correctly set up machine and MPI library, it's actually pretty easy to use that. You don't really have to worry about whether should I move this data into the main memory before sending it. MPI will take care of it. And yeah, so for that, we also have a small example that you can play with and run on the on Cooley. It's actually require a slightly different MPI implementation, and you also need CUDA in this case. So if you use the software environment to load these two library, you should be able to build with the makefile in our example. So far, any question about the GPUs side? No question? Okay, cool. So the last thing that we're going to cover is the new stuff that we're introducing in MPI-4. So MPI-4 standard has been approved and it's official since last year. So there are many changes, but there are a few major new features, including the persistent collectives, partition communication and sessions, and improvement in error handling and others. So I'm going to just briefly talk each of them. So the persistent collective. So as you know, we already have a non-blocking collective operation, which allows the application to overlap the communication with, basically decouples the data transfer and synchronization and allows you to overlapping the communication with computation better. So, but at the same time, because it's collective, so whenever you call the collective operation, the library still have to allocate internal data structures and the collective schedules and trees and other necessary setup to make the collective work. But if you have a application that does collective operation repetitively with the same buffer, same data type, and the same size of the data, the persistent collective is very helpful for that to further reduce the overhead of setting up the collective. So basically, you can set up the collective once, and then you can repetitively using the same collective operation to send data in every iteration if you have a loop. So that's the persistent collective. And here is a quick example of, as you can, the top one is a non-blocking collective version. Basically, we just do some computation and do a bcast, non-blocking bcast, and then do more computation and do a reduce and wait for them to finish. Okay, and because this is in the IBcast and the iReduce, every time the application calls them, they have to set up the data structure for the collective. And because it's in a loop, it's small. It's a slight overhead, but accumulated a lot if you have run a loop like many times. Then with the persistent collective, instead of doing that, the IBcast and iReduce will be using the MPI-bcast init and MPI-bcast reduce. So to create two persistent collective requests. So when you create them, you have to identify already where the buffer is and what is the communicator and data size and all that information. And then inside the loop, you just simply do MPI start with these collective requests. It will, because everything is set up, it will just go and push the data over the network. So you don't pay the cost of setting the collective every time you do it. Okay. So the second one is partition communication. Partition communication is actually originated as a way to optimize for multi-threaded communication, right? So the idea is if we have a large buffer, we can have multiple threads to fill the content of buffer. So if they can each get a small portion of the buffer and each thread can indicate that my portion is ready for send, then we don't have to wait for the entire buffer to fill before sending any data. So that would reduce some of the overhead of synchronizing these threads. So what it does is it introduces several new functions. One is the MPI piece and in it. This is creating essentially a persistent partition request, but the addition is the partition parameter here. So you're indicating that I have this buffer and it has a number of partitions. For example, if you have a 16 thread, you can put 16 here. Then it will basically divide this buffer into 16 parts. And then the next API is the MPI-P ready. Basically, this one is going to take one of these partition communication requests and indicating a specific partition by its index is ready for sending. And then at the same time, for the receiver side, you have a MPI-P arrived function that allows you to query for a partition communication and see if specific partition has arrived. So when this in action, so this is a example of using OpenMP. As you can see, before we go into the OpenMP parallel region, we create a partition request with a certain number of partitions, and then inside of each parallel for loop, we basically just fill in the partitions and mark that as a ready, and we can test the request for completion for this from the sender side, and the receiver side it can simply just do a p-receive with different partitions and test for completion. So in this case, we're not using multiple threads to do the receive on the receiver side, but you can do that, and having each of the thread to use MPI-P arrived to check whether a partition that destination for this thread has arrived. So this is kind of a similar way that the traffic from different threads are being isolated. So internally, for the MPI library, it's also possible to have the data being transmitted through different set of network resources, so that there's no contention between different threads. Okay. All right. The third big new things is the MPI sessions. Okay. So this is a change of how MPI library is initialized. So traditionally, we do MPI init or MPI init thread to initialize MPI library. This works traditionally, but in reality, if we're dealing with multiple different libraries or different tools using MPI in the same application, then each of these libraries would have to at least check whether MPI has been initialized, and then go. If it's not, then someone have to go in there and initialize it, and then create a communicator and share it by all of them, which is very complex to get done correctly, and having all the library to work together and in a coordinated fashion on that. So with MPI sessions, instead of having MPI to create one communicator and share by all the libraries, what can be done is each library that uses this MPI in the application can use the MPI session in it to get their own handles to the MPI communicator, so they can essentially initialize separately. And also it comes with the benefit of some of the library may not need a MPI COM word that includes every process in the application, maybe only a subset of them. For example, if I have a 100 process application, maybe I'm using 90% of that for the simulation, while the other 10% is doing a visualization or analysis. Then before we will have to create a large communicator, and these two parts will have to coordinately split this communicator for each of them to use. But with MPI session, these two parts can basically request for a COM word of 90% of all the process and COM word of 10% of all the processes, and to without actually coordinate with each other on that. So like I said, basically is instead of having a initialized MPI, we're getting a MPI sessions, and then then we can query the runtime to see what are the processes available, and create a group of the process that we actually need, and then create an MPI communicator from it and go with it. So these are the major updates. There's also smaller changes, but also quite useful. One of these is bit count. So MPI MPI communication functions have these integer of counts of indicating how many how large is the data. So that is limited by the type of int. So the MPI-4 introduced these big counts interface donated by these _c suffix in the function name. Basically, instead of using an integer, it will use a MPI count type for the count variable, which supports larger than 32-bit integers. And smaller new feature number 2 is the non-catastrophic error. So this is an attempt to improve the error handling inside of MPI. So existing MPI before MPI-4, if you're doing a MPI communication and something happens, the library basically treats the state as corrupted and not then basically saying the entire MPI library is no longer good for communication. And at that point, you basically just have to to preserve whatever working data you have and then kill the program and come start again. But in reality, many of these errors may not be that fatal per se. For example, if I try to do a non-blocking communication, but the MPI library has exhausted the pool of available requests. So the communication wouldn't happen, but because it's just because the error is related to exhaustion of the request resources, then if the existing application keeps going, at some point someone else who holds who has a on-the-fly communication may finish and then release that request. Then there will be one more request in the request pool. Then the failed one, the failed MPI operation should be able to come back and retry and be successful after that. So the introduction of non-catastrophic error is now we basically as a library we'll be able to identify which errors are non-catastrophic, meaning that if this error happens, the state of MPI library is still okay for further communication as long as the user be able to come back and retry and recover from these errors. So these mostly related to a resource exhaustion. For example, cannot allocate memory or cannot allocate a request. But then basically it's more of a quality of life changes where the user can handle this operation and try to recover from them without killing the entire program. So there's also improvement to the topology support in MPI. This is mainly related to the MPI com split type function, where there's two modes being introduced. One is the guided mode. Basically, it's a set of info keys that allow user to create split communicators based on the hardware hierarchy. For example, if I want to create a split com of processes that share the same NUMA node or share the same network card or share the same GPUs, that can be done. And also there's unguided mode, which basically you have to start from existing communicator and split one level down one by one, depending on the topology level that is available on the machine. Okay, so that's the topology improvement. And we also have new communication relaxation hints. Like I mentioned, some of these we already seen, the no any tag and no any source. Basically, these hints basically the user is saying I'm not going to use any tag or any source as a parameter for communication that happens on a communicator. So the library can ignore those cases and can internally optimize. This is especially useful for multi-threaded communication. And the other two, the exact length and allow overtaking, is also similar. So the exact length is basically saying the receive buffer has to be the exact size of the message. So if you have a larger buffer, so MPI don't have to check for the buffer, so reduce some overhead. And allow overtaking is also useful for the message that ordering is not required. So if you have strictly you have all the message matching figured out by using different communicators or different tags, and then you can safely tell MPI that you don't have to maintain the ordering. The ordering, the application should be fine if the message are overtaking each other. Okay. So then there's improvement to the MPI-T events. This is related to the MPI tools interface, where now there's new a callback-driven event interface where allowing the MPI tools like profilers and debuggers to register a callback function and be able to query more information, internal information from the MPI library. Okay, so that's all I have about MPI, and this is all for the tutorial today. So just basically, for programming with MPI is the important thing to get is parallelism. It's very important for running efficiently and getting a good performance on large-scale system today. And MPI being 30 years old now and still is the standard model and widely adopted in both industry and academia. Again, your application can be next. And remember the important thing, with all this interface, the important first step is always look at your problem and see how you can decompose the problem into a multi-process version, and or a, if you are more comfortable with threading, maybe decompose it into a multi-threaded version, and then later on scale it out to multiple processes. So that's all. And here's some information that we showed before that is useful. MPI standard, which is also, I have sent a link to the Slack channel. So if you want to check out the latest standard, there you see it. And we also have several MPI tutorials, including the previous ATPESC tutorials available online. So you'll be able to check out the recording for that, and a few useful books about MPI and generally parallel programming models. And that's everything. And thanks for joining with us. If you have any question, feel free to ask. And yeah, go ahead.
So do you foresee any of the fault tolerance proposals making their way into the MPI standard?
Sorry?
Do you foresee any of the fault tolerant proposals making their way into the MPI standard?
Fault tolerance in MPI, in UFM and re-init, maybe?
Yeah.
Yes, well, as far as I know, the fault tolerance working group is pushing hard on that. Originally, we wanted to have that in MPI-4. That didn't happen, apparently. But the forum is still working on that, so hopefully it can get in the next big update on the MPI standard. But again, if you're interested in, I would encourage you to join the fault tolerance working group call, because like we as a software developer on the programming runtime side, we have certain way of looking at the problem, which may or may not be the way that application developer really needs. So we always say that the forum is an open place for not only the MPI developers, but also for the application developer to come in and tell us what feature matters the most to you. And if fault tolerance is something that you really want, that the MPIs really need to have, and please tell us on MPI forum, so we know how we can shape the MPI standard the best way to serve the applications. Yeah. Any other questions? Not sure which one is first. Okay.
Is there any way that you can exchange information within a session or within 2 sessions?
Within.
So, like, if you have multi-physics or something, and you have a session for like one piece of the problem and a session for another, is there any way that at some point you could exchange?
Oh yeah. Certainly, you certainly can. Well, the simplest case, you can both create a communicator of all the processes, and these, like the example I have, like the 90% for simulation and 10% for analysis is just a simple example. It doesn't have to be that way, right? You can even have like 100% for simulation and also create another one, but with less process, also doing the analysis. Right? There's nothing prevents you to have overlapping groups. If that answers your question.
Are non-blocking sends and receives expensive enough in practice that I should consider parallelizing if I have a lot of them, or is it not? Or should I just run them all serially?
Sorry, I didn't.
Parallelizing using threads, or
Yeah.
so if he has many non-blocking sends and receives, should he issue them all from one thread or from multiple threads of speed?
In assuming when you're doing them on thread, they're using different communicator, so they actually have isolated stream. It could be beneficial on certain machines. Because what we see with the network is really fast, and the actual overhead of sending the message through the native path is really low, and sometimes you need more than one CPU cores to actually saturate the message rate. So in that case, instead of having one thread doing multiple send and spread that out to multiple threads might be beneficial in terms of message rate to saturate the network. But in the same time is like if you only have one process on node, it's probably beneficial. But if you have multiple of them, it's at one point you're going to be bounded by how many messages that the network can really handle, and after that. Beyond that point, then having more issuing capability may not be getting you a real benefit. Okay.
In the sessions where when the RAMs are created.
When in sessions.
Yeah, I mean you can have multiple sessions.
Right.
And when you initialize a session, you create the RAMs.
No. So you create a communicator, right? So the difference is that traditionally we do MPI init, we get an MPI COM word. That's all the processing there, right? So right now the MPI session init doesn't create the COM word, but you will be able to see all the live processes in there, and you can go in and say I want these processes and create a group, and then derive a communicator from that group. So instead of having a COM word that contains every process, then you have a smaller COM word that only contains those processes.
So you spawn the processes in the MPI-4, and you can use fewer processes if you want, but no more processes that previously spawned.
Yeah, no more than MPI execs, the dash n.
Okay.
Yeah.
Thank you.
I would encourage everyone to keep doing the hands-on, finish where whatever you haven't been done in either the RMA one or the threading one, or maybe if the derivative did have one, if you don't have the time to finish,